Hello, my name is Carmon, and I will present joint work with Ben-Sasson, Yuval Ishai, Swastik Kopparty, and Shubhangi Saraf on proximity gaps and correlated agreements for Reed-Solomon codes. We will begin with basic definitions of Reed-Solomon codes, a motivating problem, and we will get to our theorems. Reed-Solomon codes are linear codes from an evaluation domain D to a finite field Fq in which it lives, which are evaluations of low-degree polynomials, degree up to k, with coefficients from the field. We call the space of all functions D to Fq the space of words, and we denote by n the block size of the code, which is the size of the evaluation domain D. We also denote by rho the rate of the code, which is k plus 1 over n, which satisfies that for every row n points, there is a unique code word interpolating the values at those points. We denote by delta the relative Hamming distance in FQD, which is the number of disagreements between two words relative to the size of the evaluation domain. So it's always a number between 0 and 1. We also denote by delta the distance from the code itself, which is at most 1 minus rho, because there is always an interpolation for any row and points. We use delta to denote a distance parameter, and we will say that two words are delta close if the distance between them is at most delta, or delta far if the distance is more than delta. And similarly, we will say that a word is delta close to the code if the distance to the code is at most delta. Epsilon will denote an error parameter, which will appear later. Our main motivating problem is to verify that two words U0 and U1 are simultaneously cowords, or that they are simultaneously delta close to the code. And we want to do this in a way that is more efficient than checking each of them separately. An idea by Berlekamp, Welch, and Decoders is to verify instead that a random linear combination of the two words is delta close to the code. One reason that this can be what we want to check is that computing this random linear combination is a local procedure and can be done in a distributed way. It depends for every x in D just on the values at x. Another reason why this might work is that if we assume that U0 and U1 have correlated agreement, which means that not only are they separately each delta close to the code, but they also agree with code words on the same set of points of density 1 minus delta inside D, then so does the random linear combination. It will also have the same correlated agreement with them on the set of the same size, and so it will also be delta close to the code. But is the converse true? Is it true that if for a random linear combination we have it be delta close to the code and we verify that, does it guarantee that we should actually expect U0 and U1 themselves to be delta close? Is it necessarily the case? And the answer is yes. And we of course have to assume that it happens with a large enough probability. It may be the case that just for a very specific z, for example, z equals 1, U0 plus U1 is delta close to the code, but that doesn't say anything about U0 and U1 themselves. We have to assume something about quite a lot of z's in order for this to happen. And how many z's we will need will depend on the parameters, on n, q, rho, and delta. And our statement will only work for delta up to 1 minus square root rho. More formally, for any two words U0 and U1 and the distance parameter up to 1 minus rho, we assume that the probability for a random linear combination to be delta close to the code is at least epsilon. So that means that for at least epsilon times q values of z, we will have this linear combination be delta close to the code. Where this epsilon is very small and explicit and will depend on the parameters, we will see exactly how in a few slides. Given this assumption, then it is the case that U0 and U1 will have correlated agreement, which means that there exists a set D prime, subset of D, which has relative density at least 1 minus delta, and code words V0 and V1, which agree with U0 and U1 on the subset D prime. So this is exactly the correlated agreement that we have on the subset D prime with the code V. And if this is the case, as we said, then in particular, the combination of U0 and U1 will be a distance at most delta from V for every Z in FQ. We will have agreement on the set D prime, and the disagreement will only be outside D prime, which is of relative size at most delta. So let's focus just on the last part, forget about the correlated agreement, just focus on the fact that for every combination, the distance is at most delta. So this is actually a statement about the set of all linear combinations. This set is a line. For U0 and U1, we have an affine line, L, that passes through U0 in the direction of U1, which is the set of all such linear combinations. And our assumption was that for a random element of this line, chosen uniformly, the distance from the code was at most delta with probability greater than epsilon. And if this is true, then it follows that the distance is actually at most delta for all elements. So there is a dichotomy here, which we call a proximity gap, the affinite feature proximity gap, which means either that the probability of the distance being at most delta is at most epsilon, or if this probability is equal to 1. So either all elements of the set are distant at most delta from the code, or only very few of them can be at this distance, and almost all of them will be delta far from the code. A different way to say this, if we focus specifically on the delta, which is the maximal distance of any element in the line from the code, and we see that almost all elements have to have this distance. Very few of these elements can have distance which is smaller than that, at least assuming that this distance is within this range of 1 minus square root rho. And we call this property that the maximal case is actually the worst case, is the very common case. We call this concentration bound on the distance. So what is this error term epsilon? We have two different ranges. We have the unique decoding distance. So for delta up to 1 minus rho half, this is the regime in which there is a unique, if there is a code word that is delta close to u, it's unique. In this range, we can take the error term to be just n over q. So this means that for the theorem to have any meaning, q needs to be at least of size n. Otherwise, of course, if epsilon is greater than 1, then there is no content to this statement. But for any epsilon which is less than 1, there is some interesting content here. And as long as q is at least linear in n, we see that there is a real substance here. For greater delta than that, for delta up to the Johnson bound, up to 1 minus square root 12, which is also called this least decoding distance, because this is the distance where we know that the size of the list of all possible decodings within this distance is bounded in some way. Then we get this theorem with an error term, which for fixed rate and delta is of a form n squared over q, meaning that if we want this to have content, we need the field size to grow quadratically with the block size. Of course, as delta approaches this 1 minus square root rho, this will have to explode, because we can't really say anything yet about this domain with delta even equal to 1 minus square root rho. So the Constantinian here will grow to infinity as delta approaches 1 minus square root rho. We'll also note that in this unique decoding distance, the rate of n over q is effectively optimal. If we replace n over q by delta times n over q, then the theorem will no longer be true. It's possible that that few elements are closer than the maximal distance for such small error term. We can also generalize this theorem by replacing the lines that all of these theorems were discussing by different sets. So instead of lines, we can have affine spaces, which are linear combinations of more than just two elements. We have the linear combination of L plus 1 elements with L different coefficients in FQ. And a different way to take linear combinations of L plus 1 elements is in a parameterized curve, which has just one parameter of z, but it is raised to different powers as coefficients of the different points. And the theorem is true also for these two spaces. If we take a random element of the affine space or of a curve, and we see that it has distance at most delta with probability greater than epsilon, then all of the elements will actually have distance at most delta, and there will actually also be necessarily correlated agreement. We also note that the error term is the same, exactly the same error term is used for affine spaces, and for parameterized curves, the error term is increased by a factor of the degree of L, which is not that bad. These generalizations also allow us to generalize the problem of reducing a linear combination of two elements, verifying two elements by verifying a linear combination, we can similarly reduce verification of L+1 elements into verification of just a single element. Prior work on this subject includes, of course, Rothblum, Vaden, and Vigdorsen, which, as we said, originated this approach. They only had delta go up to 1/2, and there was also a doubling factor. So instead of saying that if a linear combination is delta closed, then each of the elements is delta closed, the only statement was that each of the elements has to be at most 2 delta close to the code. Then there was a paper by Emis Chazai, Ishai, and Dankita Subramanian, which had delta go up to 1/2 the unique decoding radius. In private communication from Roth and Zemmel, in 2018, this 1/2 unique decoding radius improved to 2/3 of unique decoding radius. And Ben-Sasson, Kopparty, and Saraf in 2018 managed to get delta all the way up to 1 minus the cube root of rho. And later, together with Goldberg in the Deep Fry paper from 2020, we managed to improve this into 1 minus cube root of rho. And our new result, of course, up to 1 minus square root of rho. We'll also note that of all of these results, our new result is the first one that fully covers the unique decoding radius case. Some applications of these results are to soundness of communication efficient proof systems that use the Fry protocol, such as Starks, which are of particular interest to us, Ligero, Aurora, Fractal. The improvement here is that the proven soundness very much depends on what remains of 1 minus delta. So this cube root of rho actually translates to every query giving us 1/3 log rho bits of confidence that our original words were actually code words. And the new improved bound means that this 1/3 log rho is translated into 1/2 log rho, which means that we will need 33% less queries in order to get the same level of security and same confidence that we actually had code words and not just random words. There are also applications to secure multi-party communication protocols and verifiable secret sharing, where the fact that these linear combinations are locally evaluated and can be distributed is very important. And some of the applications can also only use the case of unique decoding radius results. And there are many, many more other applications. So in the rest of the talk, I will give a quick sketch of the proof and the main ideas in it. The main tool that we use is decoders, which are just algorithms that take as input a word and distance W and give us all code words from the Reed-Solomon code, which are delta close to W. And for delta, which is at most the unique decoding radius, we can use the Berlekamp Welch decoder, which returns, of course, a unique decoding. For delta, which is up to the Johnson bound, 1 minus square root rho, we use the Guruswamy-Sudan decoder, which returns multiple decodings, as the least decoding in this case is longer than 1, and is necessarily more complicated due to having more decodings. So what exactly do you use these decoders for? So we have a word u0 plus u1 times z, where z is a formal variable. And we can think about it as a word from our evaluation domain to the space of rational functions in Z. In this case, there are actually linear polynomials in Z, but if we want to consider it as a field, then it would be a field of rational functions, where for every x, we get just the linear combination of 1 and Z with coefficients u0x and u1x. What we know about this word is that if we substitute, instead of the variable Z, some elements of FQ, then for many such substitutions, we get a word that is delta close to Reed-Solomon code over the final field FQ. The motivating idea, as we said, is that if this happens for many Z's, then this can't be by chance. It can't be that these words are independent of each other. It has to be because there is some underlying correlated agreement, because U0 and U1 actually have decodings which agree on the same set of density 1 minus delta. Otherwise, there is no chance that so many linear combinations will all be delta close. And if that's the case, then that means that the word v0 plus v1z, again, in the space of words from D to FQZ, is actually a code word in the Reed-Solomon code over FQZ. And more than that, it's a code word which is delta close to W, where the distance from between these two words is exactly the distance in terms of correlated agreement. And if this is the case, if W is delta close to a code word in this space, then that means that we can try to run the decoder on it, and it should work in this case. So that's what we do. We run the decoder and we analyze the results of the decoder, and we prove that it actually decodes as V0 plus V1Z. And if it's able to decode that way, this is actually equivalent for there to be a correlated agreement, which will give us the proof of a theorem. So let's get a bit more in depth about Berlekamp Welch. How does it work exactly? So given a word W in the space of words and distance up to the unique decoding radius, we write E for the number of errors that we have, which is just the distance times n. We start by searching for polynomials A and B, such that the degree of A is at most E and the degree of B is at most K plus E. And we satisfy for each x in D the equality that B of x is AX times WX. So how do we search for such polynomials? We look at their coefficients. We write the coefficients A0 to AE and B0 to BK plus E in the field. And we write these equations for every x in D. We expand AX and BX as the sums AI times x to the I and the sum of BI times x to the I. And we see that for every particular x that we are given, this is actually a linear equation in the AI and BI. Some linear combination of the AI is equal to some linear combination of the BI. And we have n such equations, one for each element of D. So we can write this system of equations, of n equations in t variables, where t is k plus 2e plus 2, the number of coefficients of A and B. And we can represent it as a matrix. And now we are just trying to find a null vector of this matrix, and this will give us A and B. And what we know is that if the word is actually within delta distance of the code, then such a solution must exist. And moreover, any such solution will have, which is non-zero, will have AX dividing BX as polynomials, and the ratio will be the code word that is delta close to W, the unique such code word. Now let's replace our general field F with the rational function field FQZ. So now we are looking in particular for not just one variable polynomials, but bivariate polynomials AXZ and BXZ, which again have the same conditions on the x degrees of A and B, and same condition for every x and D. But now this condition is not just in field elements; it's in field elements which are functions in Z. And we are looking for coefficients A0 to AE of Z, and same for B, which are also functions in Z and satisfy these equations for every x. But again, these are linear equations over FQZ. And the coefficients here are actually more simple than that. We just have coefficients which are constant polynomials in Z for the coefficients of B, and coefficients which are linear polynomials in Z for the coefficients of A. So the matrix is not very complicated. The matrix just has entries which are linear and constant polynomials in Z. And we are looking for solutions to this matrix, M of Z. What do we know about it? We know that for many Z's, the word W, when variable Z is replaced by some substitution, is decodable, is delta close to the code. And this turns out to mean that M of Z will have a solution, because this M of Z that we're taking our matrix M and replacing the variable Z with a substitution is the same matrix that we get if we first did the substitution and then ran the Berlekamp Welch algorithm. And this matrix will have a good solution because the word is delta close. We still don't know that W is a priori delta close. We don't know what will happen with the code, with the decoding. And we will have to answer many questions. We will have to answer the question of, is it even true that solutions to this equation must exist? And is it true that if they exist, then they satisfy that A divides B? Because in the end, we're looking for the ratio between B and A. Is it true that if they divide each other, that the ratio must be of the form V0 plus V1Z? So specifically, we're requiring that the x degree will be at most K for V0 and V1 to be code words in the Reed-Solomon code. And just that this will be a linear polynomial in Z and not anything more complicated, not a polynomial of 5 degrees in Z, not generally it actually should be even a rational function in Z. And above all, will this ratio actually be delta close to W? The answer to that one is actually pretty much guaranteed from the decoding. But once we answer yes to all of these questions, then we have that V0 plus V1Z is a decoding of W, which means there is correlated agreement, and that will give us a proof. So that's basically the proof strategy. We study all of these questions, we answer yes to all of them, and this gives us the proof of the theorem. For the Guruswamy-Sudan decoder that we use for the more general case up to 1 minus square root rho, the approach is similar, but the decoder is more complicated, more deeply algebraic, and therefore the proof is also more complicated and requires deeper algebra. And thank you very much for listening.